Okay, what we're going to look at in this section is population models, logistic modeling, exponential modeling, and all the kinds of things that they can do. And you'll use these a lot when you look at different sorts of populations, from bacteria to people to whatever. Logistic models are great fits because if you think about it, there's only so much space to put people, and then you run out of space. So there is a limit to how many people can live in a particular place. So the logistic model is actually an excellent way to look at that. Exponential is really good if you're looking at like half-life or bacteria growth or things of that nature. So what we've got here is a population model where P sub 0 is your initial population, R is your rate, and T is your time in years. And if your rate is greater than 0, then you're going to have growth, and if your rate is less than 0, you're going to have decay. So let's just dive into a problem. Tell whether the population model is exponential growth or decay, and then find the constant percentage rate of growth or decay. So what we want to do is, if we're just going to start with San Jose, they give us our population model, P of T, is equal to 782,248. That's the initial population. So this guy right here is the P sub 0. All right, this is your initial population right here. And then 1.0136t is the 1 plus the rate. So what we want to do is, we're going to look at it this way. 1 plus the rate is equal to 1.0136. So when you subtract 1 from both sides, you get that the rate is equal to 0.0136, which is bigger than 0. So for San Jose, it's growth. Okay, we have a population growth factor. With Detroit, initial population of 1.2 million, and so if we look at this guy's rate of growth, 1 plus R is equal to 0.9858. So when you subtract 1 from both sides, R is negative 0.0142, which happens to be less than 0. So for Detroit, we are decay. And then we want to find the percentage of growth or decay. Well, that's just looking at these first two spots. So my percentage of growth for San Jose, the percentage of growth is 1.36%. And the percentage of decay for Detroit is going to be 1.42%. So that's kind of how you're going to use exponential models and some of the different ways that you can kind of look at a different problem. And the biggest key on determining growth or decay, the biggest key is just to look at this number right here. If this number is bigger than 1, your decay. If it's less than 1, or if the number is bigger than 1, your growth, and if the number is less than 1, your decay. Okay, so we want to determine the exponential function with initial value of 12, increasing at a rate of 8% per year. And so just recall real quick what that population function looks like. And it was the population over time is equal to your initial population times 1 plus the rate to the t power. Okay, so in this case, then, when I am trying to figure all this stuff out, my initial population is 12. My rate is 8%. And as a decimal, we would write that as 0.08. And then t is t. Nothing fancy there. So I just substitute all these guys in. P of t is going to give me my initial population times 1 plus 0.08 to the t power, which is the same thing as saying t times 1.08 to the t. Or if you want to put 1.08 in parentheses, either way. But just remember that the only thing being raised to the power here is 1.08, and then you multiply by 12. Okay, so now we've got bacteria, and bacteria does follow exponential growth. So suppose we have a culture. Suppose we have a culture of 100 bacteria put into a petri dish, and the culture doubles every hour. Predict when the number of bacteria will be 350,000. So think about this for just 1 second. My initial amount, that P0 part, is 100. And then after 1 hour, it doubles. So when T is equal to 1, then I've got 200 bacteria. And then when T is equal to 2, I've got 400 bacteria. And then when T is equal to 3, I've got 800 bacteria. So it's doubling. Well, what shape is this taking? It's taking the shape right here. We're looking at that initial population times the rate that it's changing. And in this case, it doubles every hour. And so if you follow this pattern, this is what it's going to look like. Okay. Well, what does that give me then for my function? So my function over time is going to be equal to 100 times 2 to the t. And how do you solve that then for 350,000? Well, I know what my population is. I just don't know how long it's going to take to get there. So we're going to use this guy as my model for solving. And I'm just going to take my 350,000 and set it equal to 100 times 2 to the t power. And that's all there is to it. And there's two ways that you can solve this out. You can graph this guy and graph this guy and find where they intersect, which is really easy. You can use your calculator. Or you can go ahead and solve these two guys out by dividing both sides by 100. And so when you do that, you get 350,000 divided by 100, so you're going to lose 2 zeros of space here. So you're going to end up with 3,500 equals 2 to the t. And then you can rewrite this with as a logarithm. So this would be a log base 2 of 3,500 equals t. Now, we may not have learned how to do this just quite yet, but you can punch this in on your calculator. And basically what we're going to punch in is log of 3,500 divided by a log of 2. And that will get you your t value. And it should match the exact same thing that you get on your graph. And definitely graphing it is maybe a step or two shorter. But when I punch it into the calculator, I get 11.773. 11.773 what? Hours. And I'll also show you how you can find your point of intersection while using your calculator. Okay, so let's look at a half-life question, and we want the half-life of a certain radioactive substance. We know it's 20 days. There are 5 initial grams present. Use this information to create a model and find the time where there will be 1 gram of the substance remaining. So the big thing with half-life is to remember that your base on a half-life is going to be a half. And so the initial amount is this part. So it still follows all of our items that we've talked about in relation to populations. So basically what I'm going to have here is I'm going to have like 1/2 to some power t, and I initially have 5 grams to start. So my function is going to look like this. I'll just call it h for half-life. So the thing that we need to work within is that it's 20 days on the half-life for this guy. And so the time then needs to make sure, if we're looking at it in days, needs to be related back to the 20. So basically what we're going to have is that our half-life equation now is going to be equal to 5 times 1/2. And then we need to know how many times 20 gets used. So we would be t divided by 20 for my model. And this will tell me how many days until the next one. Well, using what we did on the previous problem, we can set our gram to our half-life problem to equal 1 gram. We started with 5. We're looking at this equation, so we would graph this guy on the calculator, and we would look for a point of intersection between 1 and our function. And that's going to happen somewhere around t equals 46.44 days. And you can, again, you can use your calculator to find that. Well, 0.44, that's 44 hundredths of a day. And so when you convert that all the way down, you know, if you got 44 hundredths, that would be what? 22 out of 50. Okay, and so relate that back to X number of hours in the day. So when you do this math, this is the same thing as 46 days and about 11 hours for your half-life to go from 5 grams to 1. Okay, so we want to find the altitude above sea level. For the atmosphere, where the atmospheric pressure is equal to 4 pounds per square inch. And we know that scientists have established that at sea level it's 14.7 pounds per square inch, and that the pressure is reduced by half for each 3.6 miles above sea level. So this is really similar to our half-life problem, where our air pressure is going to be equal to an initial amount, which is 14.7. 14 is not 17. Times 1/2. And then, just like in the previous problem where we had decay occurring over 20 days, this is going to occur every 3.6 miles above sea level. So we would have that distance then be divided by 3.6 miles. So we need our distance in miles. So what we want to do then is we want to know, where is our atmospheric pressure equal to 4? So what we're going to do is we're just going to take that 4 for my pressure and set it equal to 14.7 to the 1/2 power, and then you know, you would graph x over 3.6 as the exponent. And again, just like we did on the previous problem, graph this on your calculator, locate that point of intersection, and you'll see that our height is going to be about 6.67 miles. Above sea level. And that's all you got to do on that. So your calculator is really, really handy on solving these guys out. And what you're going to do is you're going to graph this guy right here, and then graph this guy right here. And when you do that, you'll find where they intersect. Okay, so what we're going to do is we're going to look at this guy on your calculator. I'm going to work this problem out on the 83 or 84. The next question I do will be on the Inspire, so that you can see both ways and how it works. But basically what we're wanting to do is figure out a regression, exponential regression that works. There's 2 ways that you can tackle this. The way that you're watching me do right now, I put the year in as the actual year given by this table right here. The other way that you could do that is the time since that year. So like 0, 10, 20, 30, 40. And you should get reliable answers both ways as long as you stay consistent in the method that you pick. So as you're watching this video, you'll see the regression formula for this guy in pink is different for the regression formula in green. And since you can see the pink regression formula, I'll give you the one that the green one should show you as well. And so that would be your population over time is equal to 80.5114 0.514, sorry, 80.5514 times 1.01289 to the t. Okay. Either way that you go, again, remain consistent. What we want to do is we want to check the year 2003. So we're either going to check 103 if you did it in years, or we'll check 2003 if you did it with those years. But you should come up with something close to an answer where it's going to be at a time. Let's see here. When you plug that guy in, and you should get somewhere close to 301 million. Or 290.8. This is if we use our model. The 290.8 is what we were guessing, or what we were actually given. So the model gives us a little bit of a different population. Okay, so on this guy, what we're going to do is we're going to use a logistic regression, and we're going to look at the populations in Florida and Pennsylvania and look at them in millions. So I'm going to do one of those guys on my TI Inspire here, which you can see and follow all the way through. And you can do the other state as well. And if you don't have the TI Inspire, then you just simply do what you did on the previous slide, which was using the 83 or 84. So, and then this time though, what we're going to look for is a logistic regression. So that's the only big difference. And it really isn't that hard to do once you get going on the Inspire. We've done several regressions before in this course, and you can always visit my YouTube channel to get some more other ideas on how to do this. So that's how this is going to work for this particular guy, and and then it's going to give us the logistic model, and we can use that model then to estimate or take a good guess as to what the population of Florida and Pennsylvania is going to be. And remember, when you're talking about populations in Florida and in Pennsylvania, there's only a certain amount of space that those two states can fill. And so at some point, the populations in those states have to level off. And that's why the logistic model is a really good model to use when you're looking at populations of people.